This lecture will focus on the calculations that are associated with making various solutions. In science, it is important that there's a standardized way for us to quantify the concentration of various solutions. So a solution is a mixture of a solvent and a solute, whereas the solvent is the liquid portion into which the solute is actually diluted into. In the clinical laboratory, the solvent could be something like deionized water, ethanol, methanol, or some other organic solution, whereas the solute can be a solid, such as a dry chemical, or it could also be a liquid. So when we standardize the methods in which we make these various concentrations, we're able to reproduce them should we need them again. Now in science, we standardize our measurements by measuring in grams for anything that is a solid, whereas we use liters for when we're measuring volume. An example of a common solution that's used within the clinical laboratory would be in a 0.85% solution of saline or normal saline. So we may use this in hematology or other procedures within the lab. And how you do this is you take 8.5 grams of the crystallized sodium chloride, which is a solid, and then you dissolve that into 1 liter of water, which would give you that 0.85% of your normal saline solution. In order to standardize the quantitation of a concentration, we use the term molarity. Molarity is composed of 3 parts. This includes the gram weight of the solute's gram molecular weight, as well as the solvent quantity. The gram weight of the solute divided by its gram molecular weight is referred to as a mole. A molar solution refers to a solution with a particular molarity. For example, a 1 molarity solution contains 1 mole of solute that is dissolved in 1 liter of solution. Often in the laboratory, the concentration of the solution that is necessary for a particular experiment and the quantity of that solution that is needed is already known. But what you don't know, and you have to compute and figure out, do the calculations, is the amount of solute or the moles that is needed in order to achieve the particular concentration of the solution that you desire. To calculate the amount of moles needed for a solution of a particular molar concentration, then we've got to know the gram atomic weight or the gram molecular weight of that element or compound that is needed. So we've got to find that, and in order to do that, we have to find these weights using either a periodic table or some sort of table that lists the gram atomic weights of the particular element. The molecular weight of a compound is the sum of the atomic weight of each of the elements that are within that particular compound. And so the periodic table will actually list each element by the categorization of the elements according to their atomic weight, their energy level, and the electron orbital position of that particular element. And just a side note for the purpose of this lecture, the atomic weights have been rounded to the hundredths position. And because they have been rounded, when we're deciding the quantity of significant figures for results in a calculation involving an atomic weight, the preciseness of that atomic weight is ignored by this particular decision. So you will see everything moving forward rounded to the hundredths position. Here we have an example where we want to determine what is the gram molecular weight of potassium chloride. So first we need to understand that gram molecular weight is the sum of the atomic weights of the potassium and the chlorine. So first we add those two together, which will give us the gram molecular weight of potassium chloride is 74.55. Many of the compounds that we use in the laboratory consist of more than just 1 or 2 elements. So in order to calculate the correct mole concentration or the molarity of that particular solution or compound, first we need to make sure that we calculate the correct molecular weight of that compound. So for example, if we want to determine the molecular weight of trisodium phosphate or TSP, then we would first need to make sure that we calculate the correct gram atomic weight for each of those particular compounds and in their combination within that particular solution. Now, trisodium phosphate is actually it's actually a white granular crystalline solid that's It's very soluble in water, and what it does is actually produce an alkaline solution. And TSP is actually used in a lot of cleaning agents. It's a builder, lubricant, food additive, stain remover, degreaser. So it has a lot of uses. So our first step is to determine the gram atomic weight of each individual element. So if you were to use your periodic table, then we would get those particular weights of the sodium, phosphorus, and oxygen. And we know that within the trisodium phosphate that we have 3 sodiums. We also have 1 phosphorus, and then we have 4 oxygen atoms. So for that particular compound, we would need to make sure that we determine that gram atomic weight for each of those compounds when they're in that solution in multiple sodium ions and multiple oxygen. So we would multiply our gram atomic weight of our sodium times 3 because we have 3 of those, and then our oxygen times 4 because we have 4 of those, and then we add all of those up together, which is going to give our total gram molecular weight of that particular compound for trisodium phosphate is 163.94. So we've already discussed how to calculate the gram molecular weight of a compound, how to determine a molar quantity, and how to calculate the actual molarity. So a solute with a molarity of 1.0 has a 1.0 mole of solute in 1.0 liters of solution. So these are things that we already know. Now when making solutions, you usually know the molarity that you want and the particular volume that you want. The only thing that you really don't know is how many grams of that particular solute do you need to make that particular solution. So now let's use our previous calculation for our trisodium phosphate and determine exactly how many grams of it will we need in order to make a 1.00 liter of a 0.200 molarity or a 0.200 molar solution. So in this particular example, we already know our gram molecular weight. We know that 1 mole equals X grams per gram molecular weight. So what we're trying to figure out is this: how many grams of the TSP do we need? So we know that 1 mole is going to equal that particular quantity, which means that 1 mole equals X grams of TSP over its gram molecular weight, which is here. So this is what we know. Now what we need to do is substitute these quantities into the molarity formula to solve for the amount of grams that we actually need. So once we substitute those into place, then we're able to work out this calculation. So we know that we're trying to figure out the 0.200 molarity. And so we're going to plug all of those numbers in. So you can see here where it's been kind of worked out for you, where we've got solving for X, and we've got that gram molecular weight into that equation. From there, you will work the algebraic equation out to come to a total of needing 32.79 grams in order to make this particular solution. So in order to make the solution, if you're going to prepare 1 liter of that 0.200 molar solution of the TSP, you're going to have to actually weigh out the 32.79 grams. So you would use your laboratory scale to weigh that out, and then you're going to place it into a 1 liter flask, and then you're going to place a little bit of water in there and dissolve it, and then you're going to continue to fill up that flask until you reach that 1.00 liter calibrated mark on that flask, and then that's going to give you the solution that you desire, that molarity solution that you're looking for. Another term that we often use to quantify a solution is normality. Normality is different from molarity because it accounts for the dynamics of the interactions of the dissolved solute with that particular solvent. Now, normality of a solution differs from molarity because it is determined by the number of equivalent weights per liter, not just using the moles per liter. So what an equivalent weight is the amount of replaceable hydrogen or hydroxide ions or a particular charge of the element or the compound. So the amount is usually reflected by what the valence of that particular element or compound is. And then the equivalent weight is calculated by actually dividing the gram molecular weight of that element or compound. So remember, you've got to add up, if there's multiple things, you've got to add those up. And then after that, then you will plug all that into the equation, and then you will determine the gram equivalent weight. So let's do an example where we try to determine the gram equivalent weight of hydrochloric acid. So we've got to get that gram molecular weight first. So we know that hydrogen, if we were to look at our periodic table, hydrogen is going to be 1.01, and a chlorine is equal to 35.45. So when you add those up, that's what's going to give you the 36.46. Now, this particular solution, the hydrochloric acid, has one replaceable hydrogen ion, so we would add those up to get the gram molecular weight, divided by that valence of 1. And of course, this is a pretty easy one. Now let's move on to something a little bit more difficult. So first we need to determine what is the gram equivalent weight of calcium chloride. We need to determine the gram molecular weight. So we need to determine those. We've got the 1 calcium, the 2 chloride, and then that's going to give us a total gram molecular weight of 110.98. And then we have 2 replaceable chloride ions, so that's going to give us a valence of 2, so you could look that up in the textbook in the little chart. With those chloride will give us the valence of 2, so if we work that out, that's going to give us the gram equivalent weight of the calcium chloride to be 55.49. Calculating the normality of a solution is very similar to how you calculate the molarity. Now here we have the equation listed where normality equals the number of grams of solute divided by the gram equivalent weight of the solute, and then that whole part is divided by 1 liter of solution. Now you got to remember that the gram equivalent weight of a solute is the gram molecular weight of that solute divided by that valence. Now you can break that equation down a little bit further, so this equation that's here up under it actually kind of tells you a little bit explains how it's broken down, but this is a little bit complicated to understand. So just for now, just know that you need to know the steps. First you need to calculate the gram equivalent weight, divide that number into the number of grams of solute, and then divide that result by the numbers of liters of solution. Now here we have an example where we need to calculate the normality of a solution that contains 98 grams of sulfuric acid that is in 0.250 liters of solution. So first we need to know our gram molecular weight. So with our gram molecular weight, we need to know what our hydrogen, the gram atomic weight is, which is 1.01, and of course we need to multiply that by 2. Sulfur is 32.06, and oxygen is 16.00 times 4. And then once you get that, that's going to give you a total of 98.08 gram molecular weight. And then we have 2 replaceable hydrogen ions. And then you're going to divide that by that whole number by 2, which is going to give you your gram equivalent weight. Now when you plug that in, you got 98.0 grams of solute divided by that gram molecular weight, 49.04. And then of course you divide that whole part by the 0.25 liters of solution. So when you work this out here, this is actually a 1.998 something. So when you round that, simplify those figures to the 100th position, that's going to give you 2.0. When you work that out, then you're going to get your normality is 8.0 equivalent concentration per liter. And so that's how you do your normality calculations. Now, as previously mentioned, molarity and normality formulas are very similar, with the difference that normality formula requires the gram equivalent weight and molarity requires gram molecular weight of the solute. Now, one normal solution or normality has a concentration of 1 gram equivalent per liter, whereas one molar solution or molarity has a concentration of 1 mole per liter. So what we would need to do, because they are so similar, we can actually use these terms to interconvert by using the following formula, where normality, represented as N, equals the valence times molarity, represented as M. So if we have an example here of 2.50 molar concentration of hydrochloric solution, we want to know what is the normality of that solution. So if we plug all of those in, because hydrochloric has 1 valence, we plug that in times 2.50, which is our molarity, and then that's going to give us an equivalent of 2.50 normality equal to that normality to equal to that molarity. Now, in the laboratory, we sometimes have to actually measure the physical properties of a solution. So an example of this would be if we were to do a serum or urine osmolality. So instead of measuring the molar quantities of a solution, we actually measure the molal quantities of a solution. So a 1 molal solution is similar to a 1 molar solution. So we know that a 1 molar solution is a solution with 1 mole of solute per 1 liter of solution. On the other hand, a 1 molal solution is a 1 mole of solute in 1 kilogram of solvent. So molal solutions are based on weight, not actual volume. So a 1 molal solution in a 1 liter volumetric flask may have a larger volume than it would for an actual 1 molar solution. And of course that meniscus of that solution would be above that particular calibrated line in that volumetric flask. So you can actually see an example of that listed here. So in comparison, if we were going to make a 1 molal solution of sodium chloride, we would do that by dissolving 58.44 grams of sodium chloride into 1,000 grams or 1.0 kilograms of water. And then on the opposite side of it, if we were going to make a 1 molar solution, then we would actually take that sodium chloride, dissolve it in dissolve 58.44 grams of it into our solution, and of course add the water to it till we reach a total of 1,000 mLs or 1 liter to make that solution. So with your molar solution, you're adding the water to reach that final volume, whereas with your molal solution, you're adding the water in the amount that you need by weight to that actual sodium chloride that you're going to dissolve into it. So now let's do an example where we want to figure out how many grams of sodium hydroxide are needed to make a 2.50 molal solution. We'll use the molality equation where we are determining X grams of solute divided by the gram molecular weight of that solute, and then we're going to divide that by 1.0 kilograms of solvent. So first we determine our gram molecular weight to be 40. We're going to substitute those values in. And using our basic algebra skills, we will come to a determination that we need 100 grams of sodium hydroxide in order to make a 2.50 molar solution. So in the clinical laboratory, the concentration of many of our analytes are actually expressed as milligrams per deciliter, or in cases of like electrolytes, it could be milliequivalents per liter. So it's very important that we're able to convert various concentrations of analytes from one type of an expression to another. So here we have an example where we want to determine how many milliequivalents per liter does a 15 milligram per deciliter calcium ion standard actually contain. So this problem actually contains several steps. So our first step will be to convert those deciliters to liters. So first we know we have 15 milligrams per 1 deciliter, and we know that 10 deciliters is equivalent to 1 liter. And of course those deciliters would cross each other out to leave you with 15 milligrams, 150 milligrams per 1 liter. Equivalence per liter is another term for normality. So by using the normality equation, we can determine the equivalence per liter or the milliequivalence per liter of 10 milligrams per deciliter standard. We then use that normality equation with a little slight modification to it, and you can read the details of that in your textbook. Then we substitute those numbers in, and once we do the substitutions with all those numbers, then that gives us a normality of 7.49. So therefore a 15 milligram per deciliter calcium standard is going to equal a 7.5 milliequivalent per liter of that normality solution. Solutions may be expressed in either concentration, in other concentrations besides molarity, or normality. So in the laboratory, solutions are often expressed in terms of a relative percent concentration of a solute into a solution. So there are 3 different types of percent concentrations that we can actually use in the laboratory. And in all 3 types, the total volume of the solvent is based on the quantity of 100 mLs or within grams, not just 1.0 liters or in molarity or normality concentrations. So these percent concentrations can be expressed as percent weight per volume, or percent volume per volume. And so we're going to talk about each of these individually, but do know that each of them has their own separate equation. In a percent weight per weight solution, this type of solution means that the amounts of the solute and solvents are weighed individually using a balance. It's important to note that the total is based on 100 grams of solution. The amount of solvent that must be weighed is determined by subtracting the quantity of the solute needed from that 100 grams of solution. So a solution consists of a solute and a solvent. So once the amount of solvent is determined, then the solvent and solute are combined and mixed together in a flask or a beaker. So in the clinical laboratory, deionized water is most frequently used as the solvent. So the percent weight per weight solutions are the most accurate because, unlike percent weight per volume, their concentrations don't fluctuate with temperature. However, the percent weight per weight solutions are not commonly prepared within the laboratory. In this example, we want to know how many grams of sodium hydroxide are needed to make a 30% weight per weight solution using deionized water as the solvent. To solve this equation, we use the basic formula for percent weight per weight, and then we substitute in the numbers that we know. So we know the 30% is what we are looking for our outcome. So we need to know how many grams of that sodium hydroxide do we need per 100 grams of solution. And so we plug those numbers into the equation, do our algebra. So to make this solution, we determined that 30 grams of sodium hydroxide would be dissolved in 70 grams. So we take that 100, subtract that 30, and then that will give us how much we need to dissolve in that deionized water in that beaker or flask. Now for the percent weight per volume solution, this is most frequently used, the most frequently used percent solution in the actual clinical laboratory. So for this solution, the amount of solute is actually weighed on a balance, and then you place that into a 100 ml volumetric flask, to which you'll start adding a small amount of the solvent to actually dissolve that solute. So once the solute's dissolved, the remaining solvent, which in most cases is going to be something like deionized water, is then added to that flask, and you're going to bring it up to that calibrated mark on that flask. Now the Latin term quantis satis means quantity sufficient, is often used in the laboratory to describe the addition of a solvent to the calibrated mark. So for example, you may be instructed to add a determined amount of solute to a volumetric flask, and then quantity sufficient it to the calibration mark with the appropriate solvent. In this example here, we want to know what is the percent weight per volume of solution that has 25 grams of sodium chloride dissolved in a total volume of 100 mLs of deionized water. So to solve this, of course, we're going to use our percent weight per volume. We plug those numbers in, and then we determine a solution with 25 grams of sodium chloride dissolved in 100 mLs of water has a percent weight per volume concentration of 25%. A percent volume per volume solution uses volume or liquid measurements for both the solute and the solvent. So percent volume per volume is very similar to percent weight per weight, and the total volume of the solution is 100 mLs. Therefore, the amount of the solvent is determined by this following formula, where you have 100 mLs of total volume minus the amount of solute, and that's going to give you the amount of solvent. In this example, we want to determine how many milliliters of ethanol are needed in order to make a 75% volume per volume solution using deionized water as the solvent. So the problem is solved in the same way that you would solve for a percent weight per weight and percent weight per volume. So we use the formula of percent volume per volume, substituting in those appropriate numbers, and then we work that out to determine that we need 75 mLs of ethanol. So then we need to know how many milliliters of water are necessary to finish making the solution. So the amount of water that we need is going to be determined by the amount of solvent, which is going to equal 100 minus the amount of solute. So we know that we need 75 mLs of the ethanol, so we're going to take that from the total volume, which means we need 25 mLs of deionized water mixed with the 75 mLs of ethanol to give us a 75% volume per volume of that ethanol. Now in the laboratory, sometimes we need to know, because a chemical solution may be labeled in terms of a relative percentage, but you need to know the molarity of that solution. So what we're going to do is, by using molarity and percentage formulas, you can actually do some interchanging between the different types of concentrations. So an example of this would be, suppose you find a bottle that is labeled 0.85% weight per volume of sodium chloride that's in your laboratory, and you want to know what is the molarity of this particular solution. So to solve this problem, first we use the percent formula to determine the concentration of that sodium chloride in the solution. So that percent weight per volume solution is calculated by the number of grams of solute that are dissolved in 100 mLs of solvent. So as we have it marked as a 0.85% weight per volume solution, we know that there are 0.85 grams of that sodium chloride that have been dissolved in 100 mLs of water. So because molarity is based on the concentration in 1.00 liters of solute, we need to determine the quantity of sodium chloride that's present in 1 liter. So we can use a simple ratio formula to determine this, where we use algebra and we cross multiply, and then that comes to 8.5 grams. Now that we've determined that, next we use the molarity formula to determine the molarity of this particular solution. So we know that there are 8.5 grams of sodium chloride present per liter of solvent in this particular solution. So the molecular weight of sodium chloride is 58.44. So we substitute these known values in to determine the molarity of the solution. So we use our molarity formula. We substitute in those known values, and then that will tell us that therefore there are 0.85% weight per volume of sodium chloride solution that has a molarity of 0.14 moles per liter. Now there are times in a clinical laboratory where you may have a concentrated solution that needs to be diluted in order to make a less concentrated solution. So to do that, we use the following formula whenever we're trying to make some sort of change in concentrations between two solutions. So to do that, we do the concentration of concentration 1, which would be the stock concentration, and volume 1, which would be the volume of that particular stock concentration or stock solution. And then we're going to determine the concentration of the new solution, of what we want it to be and what the volume needs to be for that particular solution. So in this example, we have a solution with 350 mLs of 2.0 weight per volume sodium chloride that we need. So in the stockroom, we have 5% weight per volume solution of sodium chloride. We need to determine how many mLs of 5.0% weight per volume of that sodium chloride solution that we have on hand is necessary in order to dilute it down to a 2.0 solution. So first we use the formula for concentrations, and we substitute in those values that we know in order to determine how to set our equation up. So our concentration and volume for our outcome, or our solution 2, we know. We also know the concentration of the solution that we have on hand. We just don't know exactly how much we need to use. So when we plug those values in for this particular equation, and then we use our algebra to work this equation out, which gives us 140 mLs of our 5.0 stock solution weight per volume that we have on hand will need to be diluted in order to make a total volume of 350 mLs. Now, because we're using the same values on each side as far as weight per volume as our percentages, and we're coming to the determination of mLs, then we don't need to do any other kind of conversions within that equation.